In this work, we present a conditional GAN framework for video-to-video synthesis at 2K resolution. Given an input video, for example, a video of semantic segmentation maps, our network transforms it into a photorealistic video, as shown here. Note that the frames are temporally smooth. Starting from a video in some source domain, this technique synthesizes a new video in a target domain using a learned network. This gives us new tools for higher-level video manipulation and synthesis. In addition to synthesizing street scenes, we show our network synthesizing videos for other domains. For example, our network can transform edge map videos to videos of human faces. Here we show some examples of synthesized people talking. Our network can generate different people speaking given the same input edge maps. Note that the results are temporally consistent from frame to frame. Another example, we can synthesize videos of humans moving given pose information. For example, we can generate videos of people dancing. Using estimated poses as an intermediate representation, we can transfer dancing motion from one person to another person. Note that even the shadows are consistent with the subject. Our network can synthesize multiple different results given the same input, or we can manipulate the input to generate a desired output video. Let's look at a side-by-side comparison between the input video and the synthesized video. For example, we can change all the trees into buildings, or edit the styles of the buildings and roads. We can generate multiple styles and apply them to objects in the video. We can change all buildings back to trees, and change their styles again. Next, we compare with two state-of-the-art methods, Pix-to-Pix HD and Coherent Video Style Transfer, called CoVST. For Pix-to-Pix HD, we directly apply the method frame by frame. As you can see, although each individual frame is high quality, the result flickers frequently between frames and doesn't look convincing. CoVST adopts simple temporal consistency constraints. Although it performs better than the per-frame result from Pix-to-Pix HD, the flickering persists. The result doesn't look temporally consistent from frame to frame. On the other hand, our result looks temporally smooth, which is much better than these previous methods. Let's see how our method works. We train our network using a sequential generator and multiscale discriminators. The generator takes in input maps and previous frames and generates an intermediate frame and a flow map. The flow map is used to warp the previous frame, which is then combined with the intermediate image to output the final frame. The final frame then becomes input when generating the next frame, and so on. We use two types of discriminators, one for images and one for video. The image discriminator takes both input maps and output images and evaluates multiple feature scales, similar to Pix-to-Pix HD. Our video discriminator takes in both flow maps and neighboring frames to ensure temporal consistency. We also subsample the frames before feeding them into the discriminator. This can be seen as multiscale in the time domain. Finally, we adopt a spatiotemporally progressive training procedure. We start with low resolution, then train at higher resolution by combining with features from the lower resolution. Similarly, we start with only a couple of frames, and then gradually increase the number of training frames. These two steps alternate, forming a progressive training schedule that enables our network to generate both high-resolution and long-duration videos. Thank you! Please find our code and models on our website.